Okay, here's some homework help on homework 1 covering operational amplifiers. So given the material that the little material that we've covered in class, I thought it'd be helpful to give you some tips. I think actually you have a lot of what's necessary to solve these problems, but I'll try to get you oriented on some of them so that you can have a profitable weekend working these, okay? So problem 1 is a problem actually that we solved today in class when we looked at the summing amplifier that had 3 inputs, V1, V2, V3, connected through 3 resistors, R1, R2, R3. So this is just a simpler case. We used KCL. Oops. So in this case, you want to use KCL to solve this, and you do KCL at this node here. And so I think that's all that needs to be said there. Okay, problem 2. First, you are to find VO. So this one is easier. This part here might be a little bit more difficult, and we'll have to talk a little bit perhaps about that in class, but I can give you a tip on it. So find VO. So again here, this is different, right? We haven't looked at any current sources yet. But what we know, we want to focus on this node here because that's where the action is. You've got current IS coming in to this node, the V minus node, and we have some current that's going to be going through RF, and then this goes into the OpAmp, right? But this current is 0, right? Because an ideal OpAmp has no current going into it. So actually we can just get rid of this, and really we only have 2 branches connecting to this node. So IS comes in to the node, and it has nowhere else to go but to go out this way. Okay, so you want to do KCL at the inverting input. Okay, and the difference between this and say problem 1 or the 3 input summer that we did in class was that in the summing case, you don't have a current source. You have a voltage source like VA and VB, but then you know something more about this inverting input. We know that because of negative feedback, its voltage will be the same as the non-inverting input, such that the voltage between those two will then, it'll be 0. And because the non-inverting is grounded, therefore we can say that the V minus voltage is going to be 0. So the current flowing, say, in from source VA is simply going to be VA minus 0 over R. So in the end, you actually have a current that is flowing in here. You could think of it as a current source, although it's not. It's made of a voltage and a virtually grounded resistor. In problem 2, we actually do have a physical current source, so we don't have to go through the step initially of trying to figure out, well, what's the current given a voltage and a resistor. It's actually a simpler problem, but it just looks different from what we've solved heretofore in class. Okay, problem 3 is can be solved simply by decomposing this using superposition. And you're going to split it into an inverting and a non-inverting amplifiers. Okay, so we did this in class, except what we didn't have in class was we might have had a voltage source that was connected straight to the inverting input, but this here may look new. But it doesn't really add any complexity if we remember that there's 0 current going into this OpAmp input. So all we have is 3 volts feeding 6 ohms in series with 2 ohms. So you have a voltage divider. So you need to figure out what the voltage is at the inverting input, which is simply a voltage division of the 3 volts. And for that part of the analysis, you don't need to even consider the OpAmp, because the OpAmp doesn't actually affect what the 2 ohm and 6 ohm and 3 volt network does. And that's because, again, there is 0 current flowing into the OpAmp non-inverting input. So it's as if this circuit here is completely detached. I'm going to put in quotes, but it's detached from the OpAmp. Effectively, it's detached. Okay, and then at that point you would replace this network, this 6 ohm, 2 ohm, and 3 volt, with basically a voltage at the non-inverting input. You could replace it with a Thevenin equivalent, but right, a Thevenin equivalent, if you have 3 volts and then a resistor here and a resistor to ground. All right, let's tie this all together here. This could be replaced with a Thevenin, which is a voltage source, V Thevenin, and then some R Thevenin. Right, and that would be grounded now, and this would go into the OpAmp. But in this case, because there's no current that goes into the OpAmp, there's no need to know the Thevenin resistance. If there was going to be current flowing, then we'd want to know the Thevenin resistance, because we'd have to count for the voltage that's going to drop across the Thevenin resistance. But because in this situation there is no current that is being supplied or needs to flow into the input of the non-inverting input of the OpAmp, it's unnecessary to calculate the Thevenin resistance, and all that's needed is the Thevenin voltage. And this you just get by voltage division. Okay, let's move on to number 4. See what my time, 6 minutes. Okay. So for number 4, you're going to practice superposition. What you want to recognize first is that right here, this is, oops, I'm going to say again, detached. It's detached from the OpAmp, again, because the current going into the non-inverting input is 0. So basically you can take that part of the circuit I just boxed off and you can solve it just like you would have solved it back in the first couple weeks of circuits. And what you're solving for is the voltage here. You're going to say this V, call V plus, and you want to find what it's equal to. You don't need to know anything about the OpAmp to do that. And it's your choice how you want to solve this. You've got 3 sources, 3 independent sources, right? VI, the 2 volts and the 0.1 milliamp. So if you want to use superposition, or you want to do some other kind of network analysis, source transformation, whatever, you just need to find V plus. Then when you have done that, then the problem is just like what you would have seen before. This just becomes one of the either inverting or non-inverting amplifier configurations, and by inspection you can just employ the gain expression for that. You know, minus R2 over R1, or 1 plus R2 over R1, and R2 and R1 are right here. The same is true now for B, except this note here, it's connected, I'll just say connected to inverting input. Okay, so be careful. Now this is not detached from the OpAmp. Now is that because there's current going into the inverting input? No. There's still 0 current flowing into the inverting input, but there's definitely going to be some current flowing through this I'll call it I feedback, right? Or IRF. Right? There could be some current there. So because there's potentially some current flowing there, we can't just ignore this OpAmp when we solve this network here over on the left. Now fortunately, we've already seen that we can say something about the voltage at the inverting input. The voltage at the inverting input is equal to the voltage at the positive at the non-inverting input. This is equal to 0 because of the grounding, right? Because of the grounding there. So actually, we can solve this circuit here by redrawing it. Right. But what do we do with this connection that is going over here to the OpAmp? Well, this is where you have to kind of abstract, and there's stuff going on that maybe you don't understand, but if you can accept this reality that for an ideal OpAmp with negative feedback, the two inputs, the inverting and non-inverting inputs, have a zero differential voltage, and because the non-inverting is grounded, that means that the inverting, this V minus, is grounded. So we could tie it to 0 volts. And effectively, for solving this, we could actually tie it to ground, okay? This is technically incorrect, but you can still solve the problem. Okay, so it's not true that it's grounded. There is no current that is flowing from this network here into ground. It's flowing toward the OpAmp, and it's actually flowing through the 10K feedback resistor. It is not going to ground. But because the voltage at the inverting input is equal to 0, if you draw a different network, which is this one here, and you ground that V minus node, you will find the same voltages and currents flowing. This current right here mainly, I'll call it I. This current I will be the same as if you had not claimed that it was grounded, but instead you just said it was at 0 volts. Okay. All right, now let's move on to problem 5. What value of R is required to obtain Vout is equal to 10 volts? So this is a little design problem, if you will, but you shouldn't be intimidated by the fact that there's 4 OpAmps. Every OpAmp circuit can be separated right here at the output. Okay, so what you have are 3 OpAmps that produce voltages. I'm going to call this VO1, VO2, and VO3. This is circuit, I'll say C1, CKT1, CKT2, CKT3. Solve each independently. Solve CKT1, then 2, then 3 independently. Then solve, we'll call the rest of this circuit 4, then solve circuit 4 as a summer, right? As a three input summer, just like we solved in class today. In fact, in class at the end, I said assume that R1 is equal to R2 is equal to R3, and you see, in fact, here they're all 100 ohms, so that's actually the case. And the 3 voltages that will feed those are not V1, V2, V3, but VO1, VO2, VO3, the 3 output voltages that you will have calculated from circuits 1, 2, and 3. Circuits 1, 2, and 3 are all just inverting OpAmps. So you already know what the voltage gain formula is for that. You just need to plug in the values for the R2 and R1 and find out what the gain or the attenuation is. So that's all that's needed for that one. Problem 6 now introduces the use of a capacitor. Okay, and you are to show that the output voltage is actually minus 100 times the integral of the input. Now you may think at first, oh, I can't do this. We haven't done anything with capacitors. Okay, well, not so. The way you're going to solve this is I would solve this using KCL right here at the inverting input. You can express what the current is going in through the 10K, this I10K. We've already solved that multiple times before. You know that the inverting input is a virtual ground because the non-inverting input is grounded. So therefore we know that the voltage across the 10K is simply VI. So you can write a simple expression for the current going into VI. Because there's only 2 branches connected to the inverting input, And knowing that there's no current going into the inverting input of the op-amp, we know that the current going through the cap in this direction here is equal to I of the 10K, right? That current has to flow right through there. It's not going into the inverting input of the op-amp. And you need to remember something about the capacitor, right? We showed today in class, brought up that IC, the current of the capacitor, is equal to C dVc dt. Right? Well, you can also write the capacitor voltage as a function of current. Okay, and I'll let you figure that out. You'll need to review. It involves an integral. Well, at this point, you have calculated what the current going through the 10K is as a function of VI. You will have then determined, okay, what is the current going through the cap once I know the current going through the resistor. They're the same magnitude, you just kind of decide on the direction, right? That'd be the only thing you can mess up there. So now this IC is really just an expression in VI in the 10K. And so this will lead you to that final expression. Okay, where are we at? Problem 7, you're to find the voltage VO, and here's a capacitor. Again, the difference between 6 and 7 is that the cap and the resistor have been reversed. Okay, so in 6 I give you the result and ask you to verify it. In 7 now you're on your own. Again, I would do a KCL here. Now if you know the voltage across the capacitor, VC, and it's a capacitance C, what is the current through a capacitor given the voltage? Okay, well, I think this is going to tell you something about what that is. So again, with this problem, you're doing KCL at the inverting input. Unlike the case where there's a resistor here at the input, and you simply look at VI minus 0 volts over that resistance, and that gives you the current. In this case, you have a capacitor. But no worries, we have the expression for current through a capacitor as a function of the voltage. So you just simply use that expression, and in your KCL in your KCL equality, right? Your conservation, right? KCL is really conservation of charge. So you're saying current going in to this node is equal to the current going out through R, and you're going to be able to write that the current going in and therefore going out is a function of VI, and it's going to involve a derivative. Okay, so you should be able to do that one. Problem 8. You have two circuits here, one not involving an op-amp. This is a very simple circuit that you could solve early on in your circuits class. And then the second one involves an op-amp. They look very much the same. The point of this exercise is that we have in both circuits a voltage source Vs and a load resistance RL, and we're interested in the voltage that we generate or that we deliver to RL. In the first case, there is no active device. An active device would be like an op-amp. All we have is a source resistance RS with Vs. It's kind of like a Thevenin equivalent, if you will. Maybe it's literally a voltage source in an RS, but maybe it's something more complex that we can just represent as Vs and RS. But in the first case, it's a simple case of voltage division. Vout is going to be less than Vs. There's nothing you can do about that. The degree to which it's less than Vs depends on the relative values of Rs and RL, and you should be able to write an expression straight up for that. For the second case, the op-amp configuration will probably initially confuse you because you see that there's no resistor in the feedback path, right? What we're used to is something like this, right? An R2 in the feedback and then an R1 going from the inverting input to ground. Well, this is just a special case. This is a special case of this, where we have let R2 go to 0 and R1 go to infinity. So if you remember the expression, this is a non-inverting amp configuration. VO is equal to something times VI, okay? This involves R1 and R2. I'll let you remember what that is. You're simply going to plug in the limits the limit values here. R2 is going to go to 0, R1 is going to go to infinity, and you're going to find that this gain expression collapses to a nice familiar number. Okay, and when you solve the second problem, you should find that VO is a function of VS, but its dependence on RS and RL may be different. In fact, it will be different than if you didn't have the OpAmp. And the point of this exercise is to show you a really important role and function that the OpAmp can serve. This circuit is representative of what happens commonly in any kind of electrical signal processing. Whenever you have some source signal, it could be a microphone, could be the output of some amplifier, and you're trying to transmit, a signal down a transmission line over a distance, you can model that in the most simple form as a voltage source and then a series resistance, RS. At the other end, where you're going to make use of that, you'll have some kind of input resistance to whatever that Thevenin equivalent would be of the network that you're connecting to. And that network receives the signal and is going to do something with it. Maybe it will retransmit it. Maybe it will turn it into something that will go out over a speaker or whatever, or display. But unless RL is infinite, which in any practical circuit, it can never be truly infinite, there will result some amount of voltage division, and therefore there'll be some voltage attenuation. And we oftentimes don't want that. So the OpAmp can help us overcome the inherent voltage attenuation, particularly when our load is less than RS and maybe significantly less than RS. Right? If I had 1 ohm for R load and I had 100 ohms for RS, that would be a bad situation. My attenuation would be close to 1/100th. It would be 1 over 101. So I would not receive much of the VS that I started with. The OpAmp can help to alleviate that issue. Okay, problem 9 is a case where it's an inverting amplifier, and we've loaded it with RL. And we've talked before, if you remember, the input, or what I've said, the output of the OpAmp consists of is just a controlled voltage source, right? With 0 ohm output resistance. However, in this case, we're going to consider a case where there is a non-zero output resistance, RO. Okay, so we're now redrawing the circuit, and we're actually going to draw the internals, if you will, of the OpAmp. Not the literal internals, because there's some further circuitry in there. Dependent sources are not basic elements. They're made up of other things like transistors and resistors. But we will then draw this RO. Okay, and so the question is, show that as AV goes to infinity, VO becomes a function of only R1, R2, and VI, and not RO or RL. But you're going to have to solve this initially for a finite AV, voltage gain, and finite RO. Okay, you don't need to know anything about op-amps to solve this circuit. Because you could redraw this circuit without any knowledge of the op-amp. This guy goes out, Ri doesn't, we say it's infinite, so we can get rid of him. And actually all we have is an R1, an R2, an RO, an RL, and a voltage-controlled voltage source, right? And that's stuff from third week of circuits. The only difference is maybe there's more nodes in there than you would have been comfortable solving early on in the circuits course. So you are to find VO as a function of R1, R2, AV, and RO and RL. And then you are to show that as AV goes to infinity, the expression for VO no longer depends on R out. So you remember that I said that an ideal op-amp has infinite input resistance, zero output resistance, and infinite gain. And what we find here is that in fact if an op-amp really does have infinite gain, voltage gain, then it's not a bad thing. It's not a limiting thing if the output resistance is not exactly 0, because the infinite gain can mask the fact that the output resistance is not quite 0. And that's what you're showing here. Okay, lastly, oh no, how many more do we have? Oh, I guess we have more problems than I thought. Problem 10. So this one, perhaps I'll say more in class. I'll give you enough for those who want to take a stab at it. It's actually not really an op-amp problem. So I mentioned at the end of class today that analog computers were the first computers to solve things like differential equations, nonlinear differential equations, and they were solved by actually building a circuit of op-amps. And the basic functions that we needed for an analog computer, or to describe a differential equation, was summing and difference. I'll call it a block, a function, a gain block, okay, and then an integrating block. And so, for instance, let's say that we had a function that said y is equal to 2x plus 3. Okay, how could I implement that? That's not a differential equation, but how could I implement that with an op-amp? Well, I would say, okay, I need a non-inverting op-amp. Let's see what I really want here. I want a gain of 2. My input's going to be x, my output's going to be y. I want a gain of 2, and I want an offset of 3. Okay, so let's try one thing. Maybe I'll do this. I'll do R and R, and then I'll put this, I will do 3 volts, and I'll call this X, or Vx. Right? So what do I get out here? If you do the superposition, when you turn X off, or Vx off, you'll get, oops, do this 1.5. Okay. We'll actually get 1.5 times whatever the gain is of the non-inverting amplifier. The gain of the non-inverting amplifier is 1 plus R2 over R1. Well, R2 and R1 are the same, so it's 1 plus 1. So I'll get 3 volts at the output due to the 1.5 volt here. When I turn the 1.5 volt off and just have Vx on, now I have an inverting amplifier. And the gain here is minus R2 over R1, so I get minus 1 times X. Okay. All right, so that's not exactly what I wanted. I wanted a gain of 2. Well, I could do 2R here, and that would give me a gain of minus 2, because it'd be minus 2R over R. But now I'd have to change this voltage here, because my non-inverting gain is 1 plus R2 over R1. So 1 plus 2R over R. So 1 plus 2, or 3. So I would need to make this 1 volt, right? 1 times 3 is 3 volts. I'm almost there, except I have this problem that X is minus, right? So this is actually minus X. And what I need to do is I would need to add an inverting stage. How do I do an inverting stage? Well, I could just do R and R, and then I could ground this. Right? Now this is an inverting stage. The gain is minus R2 over R1, which is just minus 1 in this case. So if I put in X, I get minus X out. Now when I feed minus X into the second op-amp, I will in fact get my Y equals 3 plus 2X. So that's not to do with this problem directly, but it's just to give you a little picture of how you can implement some arithmetic, an arithmetic expression, algebraic expression, using some op-amps. And what we've seen here is summing, difference, scaling. Okay, well, to implement a differential equation, you have to have a derivative in there. And so what you've already found from previous problems, you've seen this block here. This is the integral, right? So V2 is actually, this is going to actually be the integral of V1. Okay. So the other way I could write this, let's say that it turned out, and you have to work out the, plug in the values for the capacitance and the resistors. Here you want to go back to what problem? Problem 6, right? So problem 6. I'll say here, C, problem 6. Right? In problem 6, we saw that if you have 1 microfarad and 10K, actually this term here ends up being 1 over RC is what it turns out to be. Okay, so you need to choose your R and your C to get the gain here that you want. In the case of this problem here, we're given R and C. So fortunately, it looks like 1K, that's 1,000, and 1 milli is 1/1000. So when you do R times C, it turns out to be 1. How convenient. So this block here is simply the output is equal to the the output is equal to the integral of the input. So we could say this here is equal to minus, there's a minus sign, minus the integral of V1. Okay. We could also write that this here is equal to the derivative of V2. And you have to think about that for a second. But if this block right here takes the integral of whatever goes in, then if we feed it V2 dot and we take the integral, then what we get out is the integral of the derivative of V2. So we just get V2 out. Okay? And you notice that you have 2 of these, right? These are equal. So we could say that for this guy on the right, the output is V3. The input must be V3 dot. If the input to the second integrator is V3 dot, and that's also the output of the first integrator, then the input of the first integrator must be V3 double dot. Okay? And V3 double dot is equal to whatever this gain is here, right? This is inverting, so like a minus R2 over R1 times this V3. And it's a chicken and an egg. Basically, you know, since it's a closed loop, you're going to be able to write an equality that will be of the form, you know, like in a differential equation, you might come up with something like x dot plus 3x is equal to 0. That's what you're going to end up with here. And you're going to write it in terms of either V3 or V1. And it looks like, because you have 2 integrators, that you might have something more than just a first derivative term in your expression. All right, so the question is, if you assume some conditions here, initial conditions, find V1 for all time. Now this may seem complicated, like, ooh, we haven't had differential equations. Okay, this question is asked in light of you having had circuits where you did solve for the second order response of an RLC circuit, and you started out solving for the case of just an LC circuit. Well, I don't know, maybe you didn't, but that's like the lectures that I had and that are online. First solve an LC circuit, okay, no R. And I can tell you that the differential equation that shows up here is going to be something that looks very familiar, and in fact identical to something you would have seen when studying a basic LC circuit. So yeah, take a stab at that, and then you can bring up some questions in class on Monday. Okay, problem 11. You did some MOSFETs in circuits. So I'm going to let you maybe wrestle with this one a little bit. And I'm going to actually skip problem 12 now, and we'll look at that in class together. Well, no, I might as well. I'll go ahead. Okay, this has turned out to be much longer, but it should save you good time on doing your homework because you have some direction here. Okay, for problem 11, it says show that the following circuit with finite OpAmp open loop gain AV approaches an ideal voltage-controlled current source sink, voltage-controlled current sink of dependence VI over RS. So what this is claiming is that if you have an op-amp that has, in the limit, an infinite gain, then the circuit on the left behaves like an ideal controlled, voltage-controlled current source. And the way that you program this current source is you apply a voltage VI, which is this guy over here, and it forces a current IX right here. Now, of course, there'd be no current IX unless this was connected to something. So here's a practical example. Let's say I wanted to run some tests on a battery. Here's a battery, and I want to measure, okay, how does the battery voltage respond as I pull different currents from it? Well, perhaps I want to say, I want to program it, I want to test it at 1 amp. So VI, I might program to be this little pulse of current, of voltage, I'm sorry. Little pulse of voltage. And I want this to program, let's say that RS was equal to 0.1 ohms. Then if I pulse this to 1 volt, then according to this here, it would say that the current I've programmed is 1 volt over RS, or 0.1. So I've just programmed 10 amps. All right, let's say that that's what I want to do. I want to test the battery at 10 amps, not 1 amp. So I give it a little pulse from a function generator. It lasts maybe a millisecond, and I pulse it to 1 volt. And what has this circuit done? It's converted my little voltage into a very accurate current sink, current source that actually it sinks, it pulls current from the battery, and it's absorbing power actually. So if the battery is a 12-volt battery, then during the time that it's pulling 10 amps, it's absorbing basically 120 watts. Right, so it's a very practical circuit. And what you are to show in this problem is that you get this nice simple expression here if AV goes to infinity. Okay, so the way that I would solve this is, well, actually, I am going to skip on how to go through this now. I'll let you think about it a bit on your own, then we'll touch on it in class. The problem 11 and 12 are kind of tag-ons from the core set of 10 problems that make up the central part of the homework set. So on this problem 11, do some thinking on it. You'll learn more if you've actually thought through and come up with a way to solve it, but otherwise we will talk about it in class. Okay, the last one here is just a really cool, very interesting circuit. It shows some of the neat things that are possible with an op-amp. And again, on this one, I think I'm going to go through it in class. I'm not going to take time now. So if you get all the 10 problems done, that would be sufficient for the homework set until we go over problems 11 and 12 in class. So you can totally solve this. What you need to do, it tells you the hint here that you apply a test voltage Vx at this input here. So if I put a voltage right here and I say Vx, let's say it's 1 volt. Okay, you can leave it as Vx or you can apply 1 volt. And then you actually find Ix. Then by doing that, we can say that the resistance looking in is going to be equal to Vx, or a change in Vx, divided by a change in Ix. In this case, we can simply look at just Vx and Ix. So apply a test voltage, solve that circuit where you're solving for Ix, and the ratio of Vx to Ix will be the input resistance, and it's quite an interesting result. It's a fun circuit to solve. You will notice that unlike all the other circuits, this one has positive feedback as well as negative feedback. Okay, so some of the output, Vout here, goes back to the positive input, some goes to the negative. And notice also that in this circuit, we're not actually using the output. Okay, so all the other circuits we do, we're usually taking something at the output of the op-amp. In this case, we're not. We're actually just looking into this. It's really a one-port network, meaning there's 2 terminals, and we look into it, and we're wondering what is the resistance that we see when we look into it. Okay, so how do you include a positive feedback? All you need to do is if I apply, hold on a second here. If I apply a voltage Vx, right, and let's say I'm trying to solve Ix, so that's why I say apply a test voltage Vx, find Ix. Well, I know the current going into the two inputs of the op-amp are 0. So Ix is actually going right through this positive feedback resistor R. Okay, well, can I find the current going through this resistor? Well, just do Ohm's law, right? Ix is going to be equal to the voltage across it, VR over R, and the voltage across it is going to be the voltage Vx, that's on the left side, minus VO on the right side. Okay, so we have an expression now, Ix as a function of Vx and VO. But we're not done. We're now going to have to actually solve for VO. And here you can actually employ, let me use a different color here. If you just look at this part here, this is a non-inverting configuration. And you might say, wait, you're cheating because you're ignoring the resistor R, the positive feedback resistor. But as has been mentioned before, if you load the output of an op-amp with a resistor, you don't actually change how the op-amp behaves because it's a voltage source at the output. Now, what makes it particularly true in this case, R is not grounded. That's what we've looked at before. In this case, R is connected back to the non-inverting input. And so you might argue, well, if VO changes, that positive feedback resistor could go and change the voltage at the non-inverting input, and that in turn would change the output. And that's very true. But in this case, because we've applied a test voltage Vx, the test voltage Vx actually forces the voltage at the non-inverting input right here. This voltage is fixed by Vx. So therefore R and VO have no effect on it. And so for that reason, you can ignore the positive feedback resistor R when determining what VO is. And VO is simply going to be a voltage that involves a non-inverting amplifier configuration and the voltage that's at the input of that non-inverting amplifier configuration, which is simply Vx here. It's applied at the non-inverting inputs. So you'll put those two pieces together. This here will end up being some function of Vx. And once you plug that in, you'll have an Ix that's a function of just Vx. And you'll be able to rearrange things such that you can take this ratio Vx over Ix, and that will give you the input resistance. Okay, well, I'll stop there. Hopefully this proves to be helpful. And you should not have to spin your wheels on any of these problems. I mean, maybe the problem 11 will be is a little bit different type of problem that would be understandable if you spun your wheels a bit on. Problem 10 is a bit different, but I think you can do that given the help I've given you. Problem 9 takes a little more effort, but again, it's circuit analysis that you would have done in the first, in the third week or fourth week, by the fourth week in circuit, so it doesn't actually require any op-amp knowledge. And I think the other ones we've talked through enough for you to be able to have a clear path forward. So I wish you all the best in completing the problems, and I will see you in class on Monday.